In this video, I'm going to talk about the capabilities of configuration mechanisms like the Puppet, Chef, and Ansible. By now, you have seen how to use the iOS CLI to configure routers and switches. To configure using the CLI, you get into configuration mode, issue configuration commands which change the running config file, and eventually leave configuration mode. If you decide to keep those changes, you save the configuration to the startup config file using the copy running config startup config command. Next time the router or switch boots, the device loads the startup config file into RAM as the running config. Simple enough. This video discusses tools for configuration management that replaces that per device configuration process. To even imagine what these tools do first requires you to make a leap of imagination to the everyday world of a network engineer at a medium to large enterprise. In a real working network, managing the configuration of the many networking devices creates challenges. Those challenges can be addressed using that same old use configuration mode on each device process, plus with hard work, attention to detail, and good operational practices. However, that manual per device process becomes more and more difficult for a variety of reasons. So, at some point, enterprise turn to automated configuration management tools to provide better result. The first part of this video takes a generalized look at the issues of configuration management at a scale along with some of the solutions to those problems. The second part of this video details each of the three configuration management tools, Ansible, Puppet, and Chef, to define some of the features and terms used by each of them, okay? And at the end of this video, you should be able to see some of the reasons why these automated configuration management tools have a role in modern network and enough context to understand as you pick one to investigate for further reading. About the device configuration challenges and solutions, think about any production network. What defines the exact intended configuration of each device in a production network? Is it the running config as it exists right now, or the startup config before any recent changes were made, or the startup config from last month? Okay, could one engineer change the device configuration so that it drifts away from the ideal, okay, with the rest of the staff not knowing? What process, if any, might discover the configuration drift? And even with changes agreed upon by all, how do you know who changed the configuration, when, and specifically what changed? We know how to configure one device using the configure terminal command to reach configuration mode which changes the running config file, and how to save the running config file to the startup config file. That manual process provides no means to answer any of the legitimate questions posed in the previous part of this video. However, for many enterprises, those questions and others need answers, both consistent and accurate. Not every company reaches the size to want to do something more with configuration management. Companies with one network engineer might do well enough managing device configuration, especially if the network device configuration do not change often. However, as a company moves to a multiple network engineers and grows the number of devices and type of devices with higher rates of configuration change, manual configuration management has problem. This video begins by discussing a few of these kinds of configuration management issues so that you begin to understand why enterprises need more than good people and good practices to deal with device configuration. Okay, the rest of this video then details some of the features you can find in automated configuration management tools. About the configuration drift, consider the story of an enterprise of a size to need two network engineers, Alice and Bob. They both have experience and work well together, but the network configuration have grown beyond what any one person can know from memory, and with two network engineers, they may remember different details or even disagree on occasion. One night at 1 a.m., Bob gets a call about an issue. He gets into the network from his laptop and resolves the problem with a small configuration change to branch office router BR22, as you can see here. Okay, Alice, the senior engineer, gets a different 4 a.m. a call about another issue and makes a change to branch office router BR33. Okay. And after that, the next day gets busy and neither Alice nor Bob mentions the change they made. They both follow procedure and document the change in their change management system, which lists the details of every change. But they both get busy, the topic never comes up, and neither mentions the change to each for months. The story shows how configuration drift can occur, an effect in which the configuration drifts away from the intended configuration over time. Alice and Bob probably agree to what a standard branch office router configuration ought to look like, but they both made an exception to that configuration to fix a problem, causing configuration drift. In this figure, okay, we can see the basic idea. With two branch routers now with a slightly different configuration than the other branch routers. Configuration drift becomes a much bigger problem if using only traditional manual configuration tools. For instance, the on-device manual configuration process does not track change history, which lines changed, what changed on each line, what old configuration was removed, who changed the configuration, when each change was made. External system used by good system management processes, okay, like trouble ticketing and change management software may record details. However, those sit outside the configuration and require analysis to figure out what changed. They also rely on humans to follow the operational processes consistently and correctly. Otherwise, an engineer cannot find the entire history of change to a configuration. Referring to historical data in change management system works poorly if a device has gone through multiple configuration change over a period of time. About the centralized configuration files and version control, the manual per device configuration model makes great sense for one person managing one device. With that model, the one network engineer can use the on-device startup config as the intended ideal configuration. If a change is needed, the engineer gets into configuration mode and updates the running config until happy with the change. Then the engineer saves a copy to a startup config as the now current ideal config for the device. The per device manual configuration model does not work as well for larger networks, with hundreds or even thousands of network devices with multiple network engineers. For instance, if the team thinks of the startup config of each device as the ideal configuration, if one team member changed the configuration file, okay, like the Alice and Bob each did in the earlier story, no record exists about the change. The config file does not show what changed, when it changed, or who changed it, and the process does not notify the entire team about the change. As a first step toward better configuration management, many medium to large enterprises store configuration in a central location. At first, storing files centrally may be a simple effort to keep backup copies of each device's configuration. They would, of course, place the files in a shared folder accessible to the entire network team. As you can see here, we have the configuration of BR21, BR22, and BR23 in a folder in a central location. Which configuration file is the single source of truth in this model? The configuration files still exist on each device, but now they also exist on a centralized server, and engineers could change the on-device configuration as well as the text files on the server. For instance, if the copies of BR21's configuration on the device differs from the file on the centralized server, which should be considered as correct? Ideal, the truth about what the team intends for this device. In practice, companies take both approach. In some cases, companies continue to use the on-device configuration file as the source of truth, with the centralized configuration files treated as backup copies in case the device fails and must be replaced. However, other enterprises make the transition to treat the files on the server as the single source of truth about each device's configuration. When using the centralized file as the source of truth, the engineers can take advantage of many configuration management tools and actually manage the configuration more easily and with more accuracy. For example, configuration management tools use version control software to track the change to centralized configuration file, noting who changed a file, what lines and specific characters change, when the change occurred, and so on. The tools also allows you to compare the differences between versions of the files over time. Now this figure shows a sample of comparison between two versions of a configuration file. The upper two highlighted lines with the minus sign shows the lines that were changed, while the two lower highlighted lines with the plus sign show the new version of each line. Version control software solves many of the problems with the lack of change tracking within the device themselves. Okay, this figure shows output from a popular software as a service site called GitHub, www.github.com. GitHub offers free and paid accounts, and it uses open source software Git to perform the version control function. About the configuration monitoring and enforcement with a version control system and a convention of storing the configuration file in a central location, a network team can do a much better job of tracking changes and answering the who, what, and when of knowing what changed in every device's configuration. However, using that model then introduces other challenges that can be best solved by also using an automated configuration management tool. With this new model, engineers should make change by editing the associated configuration file in the centralized repository. The configuration management tool then can then be direct the copy or apply the configuration to the device, as you can see in the left figure. Okay, after the process completes, the central config file and the device's running config and startup config should be identical. As you can see here, we are configuring or editing in the central location, and automatically it will apply to the device and automatically it will save the configuration. Actually here we can see the pushing centralized configuration to a remote devices. Using the model shown here, okay, it still has dangers. For instance, the network engineers should make changes by using the configuration management tools, but they still have the ability to log into each device and make manual change on each device. So, while the idea of using a configuration management tool with a centralized repository of config files sounds appealing, eventually someone will change the devices directly. Former correct configuration change might be overwritten and made incorrect by future changes. In other words, eventually some configuration drift can occur. Configuration management tools can monitor device configuration to discover when the device configuration differs from the intended ideal configuration, and then either reconfigure the device or notify the network engineering staff to make the change. This feature might be called configuration monitoring or configuration enforcement, particularly if the tool automatically changed the device configuration. In the right figure, okay, we can see the general idea behind of configuration monitoring. The automated configuration management software asks for a copy of the device's running config file, as shown in step 1 and step 2, okay? At step 3, the config management software compares the ideal configuration, okay, or ideal config file with the just arrived running config file to check whether they have any differences. Configuration drift, okay? Per the configuration of the tool, it either fixes the configuration or notifies the staff about the configuration drift. Alright, what is the configuration provisioning? Configuration provisioning refers to how to provision or deploy changes to the configuration once made by changing file in the configuration management system. As one of the primary functions of a configuration management tool, you would likely see features like this. Actually, we are reviewing some of the features that we expect to see to have in each management or software management tool or management system actually, okay? The core function to implement configuration change in one device after someone has edited the device's centralized configuration file. Okay, the next function is the ability to choose which subset of devices to configure. All device types with a given attribute such as those of a particular role, or just one device based on attributes and logic. Okay, the next ability that we expect is the ability to determine if each change was accepted or rejected, and to use logic to react differently in each case depending on the result. And also, for each change, the ability to revert to the original configuration if even one configuration command is rejected on a device. Also, we expect to have the ability to validate the change now without actually making the change, to determine whether the change will work or not when attempted. The next ability that we expect is the ability to check the configuration after the process completes to confirm that the configuration management tool's intended configuration does match the device's configuration. The next ability maybe is the ability to use logic to choose whether to save the running config or a startup config or not. The next ability is the ability to represent configuration file as templates and variables so that devices with similar roles can use the same template with different values. The next ability is to store the logic steps in a file, scheduled to execute, so that the change can be implemented by the automation tool without the engineer being present. The list could go further, but these features outline some of the major features included in all of the configuration management tools. Now let me to explain about the configuration templates and variables. Think about the roles filled by networking device in an enterprise. Focusing on routers for a moment, routers often connect to both the WAN and one or more LANs. You might have a small number of larger routers connected to the WAN at large sites, okay, with enough power to handle larger packet rates. A smaller site like branch offices might have small routers, maybe with a single WAN interface and a single LAN interface. However, you might have a large number of those small branch routers in the network. For any set of devices in the same role, the configuration are likely similar. For instance, a set of branch office routers might all have the exact same configuration for some IP services like NTP or SNMP. If using OSPF interface configuration, routers in the same OSPF area and with identical interface IDs could have identical OSPF configurations. For instance, this example shows a configuration excerpts from a branch router with the unique part of the configuration highlighted. All the unhighlighted portions could be the same on all other branch office routers of the same model with the same interface numbers, okay? An enterprise might have dozens or hundreds of branch routers with nearly identical configuration. Configuration management tools can separate the component of a configuration into the parts in common to all devices in that role, the template, versus the parts unique to any one device, the variables. Engineers can then edit the standard template file for a device role as a separate file than each device's variable file, okay? The configuration management tool can then process the template and variables to create the ideal configuration file for each device. As you can see in this figure, in the right figure, which shows the configuration files being built for branch routers BR21, BR22, and BR22. As you can see, we have a template for branch router, and after giving the template, after populating the template with the branch 2.1, branch 2.2, branch 2.3 variables, now we have the complete configuration for each of these branches. To give a little more insight, this example, the left example, shows a template file that could be used by Ansible for the configuration, okay? Each tool specifies what language to use for each type of file, with Ansible using the Jinja 2 language for template. I will explain about the Ansible with more detail, but Ansible using the Jinja 2 language for template, okay? The template mimics the configuration in previous example, except for placing variable names inside sets of double curly brackets. As you can see, hostname, then double curly bracket, hostname. Interface gigabit 00, IP address, again double curly bracket address, and double curly bracket mask, and so on, okay? As you can see here, now we have a Jinja 2 template with variable based. Okay, after that, to supply the values for a device, Ansible calls for defining variable files using YAML, as you can see here in this figure. The file shows the syntax for defining the variables shown in the complete configuration that you have seen previously, okay, in the previous example. Hostname, address, mask, address, again mask2, RID, area, and OSPF PID. The configuration management system processes a template plus all related variables to produce the intended configuration for a device. For instance, the engineer would create and edit one template file and looks like this example, and then create and edit one variable file like this example, okay? For each branch of his router, Ansible would process the files to create complete configuration file like the example that you have seen before. It might seem like extra work to separate configuration into a template and variables, but using templates has some big advantage, okay? For example, templates increase the focus on having a standard configuration for each device role, helping to avoid snowflakes, uniquely configured device. New devices with an existing role can be deployed easily by simply copying an existing per device variable file and changing the values. Template allows for easier troubleshooting because troubleshooting issues with one standard template should find and fix issues with all devices that use the same template. And finally, tracking the file versions for the template versus the variable files allows for easier troubleshooting as well. Issues with the device can be investigated to find changes in the device's setting separately from the standard configuration template. Now let me to explain about the files that control configuration automation use them. Configuration management tools also provide different methods to define logic and processes that tell the tool what change to make to which device and when. For instance, an engineer could direct a tool to make change during a weekend change window. That same logic could specify a subset of devices. It could also detail steps to verify the change before and after the change is attempted, and how to notify the engineers users if an issue occurs. Interestingly, you can do a lot of logic without knowing how to program. Each tool uses a language of some kind that engineers use to define actions, okay? Often a language defined by that company, a domain-specific language, but they make the language to be straightforward, and they are generally much easier to learn than programming language, okay? Configuration management tools also enables you to extend the action steps beyond what can be done in the toolset by using a general programming language. This figure summarizes the files you could see in any of the configuration management tools. Include hosts, templates, variables, and actions plus program. You will learn about them in future with more detail. Alright, now let me to explain a little about the Ansible, Puppet, and Chef basics. Ansible, Puppet, and Chef are software packages. You can purchase each tool with variation on which package, okay? However, they all also have different free options that allow you to download and learn about the tools. Although you might need to run a Linux guest because some of the tools do not run in Windows operating system. As for the names, most people use the words Ansible, Puppet, and Chef to refer to the companies as well as their primary configuration management products. Okay, all three emerged as part of the transition from hardware-based servers to virtualized server, which greatly increased the number of servers and created the need for software automation to create configuration and remove virtual machines. All three produce one or more configuration management software products that have become synonymous with their company in many ways. Okay, actually, first I will explain about the Ansible, after that about the Puppet, and finally the Chef. To use Ansible, you need to install Ansible on some computer, Mac, Linux, or a Linux VM on a Windows host. You can use the free open source version or use the paid Ansible Tower server version. Once it's installed, you create, several text files such as the following: playbooks, inventory, templates, and variables. About the playbooks, these files provide action and logic about what Ansible should do. About the inventory, these files provide device hostname along with information about each device, like device roles, so Ansible can perform function for subsets of the inventory. And about the templates, using Jinja 2 language, the template represents a device's configuration but with variables. And about the variables, using YAML, a file can list variables that Ansible will substitute into templates. As far as how Ansible works for managing network devices, it uses an agentless architecture. That means Ansible does not rely on any code agent running on the network device. Instead, Ansible relies on features typical in network devices, namely SSH and or netconf, to make changes and extract information. When using SSH, the Ansible control node actually makes change to the device like any other SSH user would do, but doing the work with Ansible code rather than with a human. Ansible can be described as using a push model rather than a pull model like Puppet and Chef. After installing Ansible, an engineer needs to create and edit all the various Ansible files, including an Ansible playbook. Then the engineer runs the playbook, which tells Ansible to perform the steps. These steps can include configuring one or more devices per the various files, with the control node seen as pushing the configuration to the devices. As with all the tools, Ansible can do both configuration provisioning, configuring devices after changes are made in the file, and configuration monitoring, checking to find out whether the device config match the ideal configuration on the control plane. However, Ansible's architecture more naturally fits with configuration provisioning, as seen in this figure. To do configuration monitoring, Ansible uses logic modules that detect and list configuration differences, after which the playbook defines what action to take, reconfigure or notify. And here we can see the Ansible push model. We have inventory, templates, and variables, okay? And also here we have the playbook. We can run the playbook, and with the help of SSH or netconf, we will push the configuration to the router 1. Alright, now let me to explain a little about the Puppet. To use Puppet, www.puppet.com, like Ansible, begin by installing Puppet on a Linux host. You can install it on your own Linux host, but for production purpose, you will normally install it on a Linux server called a Puppet master. As with Ansible, you can use a free open source version with paid version available. You can get started learning Puppet without a separate server for learning and testing. Once installed, Puppet also uses several important text files with different components, such as the following: manifest, resource, class, module, and templates. About the manifest, this is a human readable text file on the Puppet master using a language defined by Puppet, used to define the desired configuration state of a device. About the resource, class, and module, these terms refer to the component of the manifest, with the largest component, module, being composed of smaller classes, which are in turn composed of resources. About the templates, using a Puppet domain-specific language, these files allow Puppet to generate manifest and modules, classes, and resources by substituting variables into the templates. One way to think about the differences between the Ansible's versus Puppet's approach is that Ansible's playbook uses an imperative language, whereas Puppet uses a declarative language. For instance, with Ansible, the playbook will list tasks and choices based on those results, like configure all branch routers in this location, and if errors occurs for any device, do these extra tasks for the device. Puppet manifest instead declare the end state that a device should have. This branch router should have the configuration in this file by the end of the process. The manifest built by the engineer define the end state, and Puppet has the job to cause the device to have that configuration without being told the specific set of steps to take. Puppet typically uses an agent-based architecture for network device support. Some network devices enable Puppet support via an on-device agent. Think of it as another feature configurable on the device. However, not every Cisco OS supports Puppet agents, so Puppet solves the problem using a proxy agent running on some external host called agentless operation. The external agent then uses SSH to communicate with the network device, as you can see here. Look at here, we have manifest, we configure manifest and on the Puppet master, and if you have the agent on the router on the device, you can directly configure the router. But if the router or the OS doesn't support the agent of the Puppet, we can use the external agent. We will send the manifest to the external agent, and here after the SSH connectivity, the manifest can be configured on the router too. Alright, armed with a manifest that declares something like this device should have the configuration state, Puppet uses a pool model, okay, to make that configuration appear in the device. As we can see here in this figure, step 1, here you can see the step 1, the engineer creates and edits all the files on the Puppet server, and step 2, the engineer configure and enables the on-device agent or a proxy agent for each device. Step 3, the agent pulls manifest detail from the server, which tells the agent what its configuration should be, okay? And step 4, if the agent device configuration should be updated, the Puppet agent perform additional pulls to get all required detail with the agent updating the device configuration. About the Chef as with Ansible and Puppet exists as software package you install and run. Chef, the company, offers several products, with Chef Automate being the product that most people refer to simply as Chef. As with Puppet, in production, you probably run Chef as a server called server client mode, with multiple Chef workstations used by the engineering staff to build Chef files that are stored on the Chef server. However, you can also run Chef in a standalone mode called Chef 0, which is helpful when you are just getting started and learning in the lab. Once Chef is installed, you create several text files with different components like the following: resource, recipe, cookbooks, and run list. About the resource, this is the configuration object whose state is managed by Chef. For instance, a set of configuration commands for a network device analogous to the ingredients in a recipe in a cookbook. About the recipe, the Chef logic applied to resources to determine when, how, and whether to act against the resources, analogous to a recipe in a cookbook. Cookbooks, this is a set of recipes about the same kind of work, grouped together for easier management and sharing. And about the run list, this is an ordered list of recipes that should be run against a given device. Chef uses an architecture similar to Puppet. For network devices, each managed device called a Chef node or Chef client runs an agent. The agent performs configuration monitoring in that the client pulls recipes and resources from the Chef server and then adjusts its configuration to stay in sync with the details in those recipes and run list. Note, however, that Chef requires on-device Chef client code, and many Cisco devices do not support a Chef client, so you will likely see more use of Ansible and Puppet for Cisco device configuration management. As a summary of configuration management tools, we can say all three of the configuration management tools listed here have a good base of users and different strengths. As for their use for managing network device configuration, Ansible appears to have the most interest, then Puppet, and then Chef. Ansible's agentless architecture and the use of SSH provides support for a wide range of Cisco devices. Puppet's agentless model, also creates wide support for Cisco devices. This table summarizes a few of the most common ideas about each of the three automated configuration management tools. Note that the column for Puppet assumes an on-device agent. Let me to review. About the action, term for the file that lists action. In Ansible, we have the playbook. In Puppet, we have manifest. And in Chef, we have recipe and run list. Protocol to network device. In Ansible, we use SSH and netconf. In Puppet, we use HTTP. And in Chef, also, we use HTTP. And about the uses agent or agentless model, Ansible is using the agentless model. Puppet is using agent with for example, agent, and also you know that Puppet also support the agentless, and Chef agent. About the action push or pull model, Ansible is using push model, and Puppet and Chef, both of them are using the for example, pull model. Don't forget, here we reviewed only about the Ansible, Puppet, and Chef. We should learn about each of them in one specific course, For example, in one course, you will learn about the features and details of Ansible, other about the Puppet, and other about the Chef.